How to solve thermal issues in compact DC-DC converter designs. Thermal issues in compact direct current to direct current converter designs can be a real challenge. These problems often come from power losses in components like semiconductors, inductors, and capacitors during their operation. Managing heat is essential for ensuring reliability and performance. So, how can we tackle these thermal challenges effectively? First, let's talk about optimizing the printed circuit board layout and thermal paths. One effective method is to use the copper areas on the printed circuit board as heat sinks. By increasing the thickness and surface area of copper around power components, you can help spread and dissipate heat more efficiently. It's also smart to place heat-generating components in a way that maximizes airflow and thermal conduction to the printed circuit board and chassis. Additionally, using thermal vapors can help transfer heat from the top layer of the board to the inner or bottom layers. Minimizing thermal resistance between the junction and ambient air is key, and careful component placement can help with this. Next, selecting efficient components and packaging is vital. Look for components that have low conduction and switching losses. This will help reduce the amount of heat generated during operation. Choosing packages with good thermal conductivity and low junction-to-case thermal resistance can also make a big difference. In some high-density converter designs, integrating copper armor plating on transformer cores can effectively conduct heat away from components, reducing temperature rise. Passive cooling techniques are another option. Attaching heat sinks directly to power transistors or other hot components increases the surface area for heat dissipation. Using thermal interface materials can improve the thermal contact between components and heat sinks or the printed circuit board, enhancing heat transfer. When passive methods are not enough, active cooling methods can come into play. Forced air cooling with fans can significantly improve heat removal, especially in enclosed or high-power applications. For more advanced setups, direct-to-chip liquid cooling circulates coolant through microchannels or jets that target hotspots. This offers superior thermal management in dense designs. Immersive cooling is another innovative approach, where components are submerged in dielectric fluids that efficiently transfer heat without electrical conduction. This method is particularly suitable for high-power or compact systems. Thermal monitoring and protection are also essential. Designing converters with temperature sensors or thermal shutdown features can prevent damage from overheating. Understanding thermal time constants helps ensure that protective measures activate before junction temperatures exceed safe limits. Finally, consider the operating environment and load profiles. Designing for the worst-case ambient temperatures is crucial, especially in automotive or industrial settings. Be sure to account for peak power loads and transient thermal effects to avoid thermal stress and potential failure. In practical applications, such as renewable energy power systems or industrial controls, these thermal management strategies ensure that compact direct current to direct current converters operate reliably within their temperature limits. By combining efficient component selection, optimized printed circuit board design, and appropriate cooling methods tailored to the application environment, you can effectively solve thermal issues in compact direct current to direct current converter designs.